today's one isn't going to be quite like that at all. This is having
Yeah,
a look
it's
at
okay.
some probability stuff. But I
Yeah,
guess as we do the breakout room stuff,
yeah,
if you want me to have a look at any of that, more
uh,
than happy
yeah,
to.
yeah. Okay then.
Cool. So what's going on here is a continuation of last week's class 2, which was on some normal distribution stuff.
Yeah.
So one of the things that we were able to identify with that was that the normal distribution pretty much applies to the
Mm-hmm.
vast majority of any probability scenarios that we come across in the real world. Um, Another topic of probability is binomial distribution, which is on the discrete side of things, when you have like very specific numbers of things. One of the things we found with binomial is that as you jack up the number of trials n, what you end up with is approximately normally distributed distributions. So if you see for like n equals 10, the overall probabilities, the distribution there is skewed in different ways depending on where the p-value, the probability of success, is. But for the same values of p, as you increase n, the number of times you do the thing, the distribution starts looking much more like a normal distribution. And so normal distribution, by the way, is just your bell curve looking things. Your grades, for instance, will be a will be a normal distribution. And so what this chapter is essentially trying to show, and it's a very small chapter, is simply that what you can do is use the binomial way of calculating mean and standard deviation and use that for the normal distribution stuff. So normally when we do normal distribution stuff, we need to figure out what the mean and standard deviation of that normal distribution is, and then plug it into the CAS functions, and that'll allow us to solve things from there. In this case, when we have something that's clearly binomial in nature, so that means only two possibilities for trials, and trials are independent. So that means basically like in this example 9, 1,000 people are sampled. Are they in favor of construction or not? So there's two possibilities there, either in favor or not in favor. And it's assumed that individually, we're told 30% of people are in favor. So you're either in favor or you're not in favor, and any given person has the same likelihood of being in favor or not in favor. Those are the two key things which tells us that a binomial probability is useful. Now, from there, find the approximate probability that between 270 and 330 people are in favor. So normally in binomial, you would do a binomial CDF for this because you have a range of possibilities. You would figure out your n, you would figure out your p, n being 1,000 because that's your total sample size, p being 0.3 because that's the probability of a quote success. And then your range of values would be 270 to 330. So if we just give that a shot on the CAS, let's clear all this. Try that again. Menu 5.5. If we're doing binomials all the way down here, binomial CDF, the n's going to be 1,000. That's our number of trials. Probability of success 0.3, and we're doing 270 to 330 because that's the domain of values we were told to solve between. And we can see that there's a roughly 96% chance that anywhere between 270 to 330 people are going to be in favor of a new freeway. That's the binomial way of calculating it. This chapter in particular is trying to use the normal distribution approximation of that. So instead of using what we just did, we now need to calculate the mean and standard deviation, which, if you have a look back at the screen share, is calculated using the binomial version of the mean and standard deviation. NP for mean, and root NP 1 minus P for standard deviation. You get those two possibilities. Then you plug that into the CAS normal CDF instead. So on this CAS, it's up here on that. I'll bring out the Casio in a minute to show you where both of those are on the Casio. The thing to watch out for here is when you're doing the normal approximation, you have to treat it like you would for any other normal distribution stuff, which may seem a bit counterintuitive. For instance, if we're doing between 270 and 330, there's not a whole lot that's counterintuitive here. There will be something that's counterintuitive a bit later. So far this is actually pretty chill. 270, 330 will be the domain. Then for mean, we saw it was 300 as calculated by the book. And then square root of 210 also as calculated by the book. And so if you hit that, you see that you get a very close approximation to what the binomial version is. In fact, you can see both of them written out on the book as well. 0.9616 is the normal distribution version, and 0.9583. Their CDF looks a bit different to mine. 270, 330. Oh, right, it's less than signs. Okay, that's why there's a little bit different. They wrote between as non-inclusive of 270 and 330. I didn't catch that. So I guess all I'd have to do is change this to be 329 and this one to be 71. 9582. Yeah, okay, that's better. So that one's not so bad. Where it gets a little bit more interesting is doing stuff like question 1. So we're told a die is rolled 100 times. What's the probability that there will be more than 10 sixes observed? So, given that we're using the normal approximation to this, we need to figure out mean and standard deviation of this scenario. So, mean in this case, NP, right? We're going to have N being 100, and then P is just going to be the probability of a 6, which on a 6-sided die is going to be a 1 out of 6 chance. So, N 100 times P, which is 1 over 6, 50 over 3 for the mean there. Then when it comes to standard deviation, well, that's just going to be square root of NP, so that's that value, times 1 minus P, which is the 1 out of 6. That gets us our standard deviation. Now, the reason why this feels a little bit weirder in this case is because when we go out and do our normal CDF, we're looking for more than 10 sixes. Normally, in discrete, that would mean that we'd put a lower bound of 11 and an upper bound of 100, right? Because we can only roll up to 100 things. I'm going to leave the mean and standard deviation as what they are, just so I can copy these into it. So let's fix that up real quick. Mean of that. Nice. Let's try that a bit better. Control C. B. There we go. And that's going to get us a decent answer. But what we end up having to do, because we're using normal distribution to approximate this, we now have to use the rules of continuous probability, which means you don't increment to the next thing, and you put your upper bound as infinity. Which obviously makes no sense for discrete, right? We can't have infinite sixes out of 100 times. But when you're using this approximation, you have to adhere to the rules of normal distributions. That's the only thing that's strange about this. It's not a particularly important topic, I would say, because every time I've seen this in an exam, they've said, don't use a normal approximation. So the only time this ever actually appears in the exam, at least the ones I've looked at, is to say, don't do this. It's in the book, so you might as well practice it a little bit, just in case, for whatever reason, they do decide to assess it. But I wouldn't put too much stock in it. Is there any questions as to what I've covered so far there? In the meanwhile, I'll just get up the other CAS and show you where those functions are on the Casio. So if we're looking to do things in a binomial way, you go to your interactive distributions discrete, because discrete is binomial, and there's your binomial PDF, CDF stuff. We're using the CDF. You'll see it's a very similar setup. Lower bound, upper bound, N and P. They label them quite strangely, but they do also have little tooltips here. So if you are to put something in here, it says POS is the probability of success. Number of trials is, well, number of trials. That's the binomial way. We won't be using that for this chapter section though. We'll be using the continuous normal. So continuous and then normal CDF, which is what you saw on the other CAS. You give your lower bound, you give your upper bound, the mean, the standard deviation. Once again, highlighting that we don't use discrete rules in here. We are allowed to use infinities, and we are allowed to be inclusive of values that we otherwise wouldn't be inclusive of. Okay, that's about it. That's, it's going to be a quite short lecture for this one because there isn't much to be discussed there. So it's the 16E stuff, and it's also the chapter summary of normal distributions. So this is just a little bit more onto what you've already been taught on normal distributions. We haven't done much practice on normal stuff, which is why this is a relatively light lecture. It's going to be more so focused on the practice of doing a few of these just to get your head around it, but more so practicing the individual topics within normal distributions. So for that, I will chuck in the Word doc on that one. This is the Unit 3.4 book, so if you haven't downloaded a copy of that, it will be also on the Google Drive in the link on the Word doc. So grab a copy of that if you don't have it. And yeah, unless there's any further questions, I'll start some breakout rooms. And I'll just go around and see how you're going with normal distribution stuff or whatever else you're looking at in school. Okay, how many have we got? 1, 2, 3. Yep. Bang, bang. Open. Cool. All right. Oh, there we go. Welcome back, Approach. I'll grab you in one. Did you cut out before I explained things? Test, test. Maybe I'll send you a message instead. Oh,
Hey, sorry.
yeah, I was just checking to make sure. Did you hear anything before you cut out?
No, I didn't.
Didn't hear anything? Okay. How about the lecture part? Whereabouts did you cut out?
I think maybe just about like 2 minutes ago. But
Hmm.
I was actually just staying back to let you know, like, I was gonna be honest with you, I'm like kind of in with the 3, 4 content right now. I'm a little bit lost
A bit
ever
lost.
since we started this probability thing. And to be honest, the reason being is when we started calculus, right? When we were doing differentiation. I had a lot of soccer going on then. I was still doing the classes, but I found it very hard to do any work on the side, like practice and whatnot.
Hmm.
Um,
Yep.
so by the time we started integration, I was still catching up on differentiation. I'm pretty good on that now, but uh I'm I'm getting to integration, and for this I'm quite lost because obviously I missed the last few lessons as well.
Yes. Okay. Understood. Understood. Okay. So what I can do from here? Let's see. How can we handle this? Um, I don't know how much I can do within just this one class, but it would be worth. Did you have a look at any of the pre-written guides or the video guides on this stuff? I guess you were catching
Yeah,
up, so.
a
Oh, you did.
bit.
Yeah.
I did do a bit until I went overseas, obviously.
Okay, so overseas, because I remember you asked me for what we were covering. So I guess did you do much of that?
No, not really. I thought I'd have time, but
Yeah.
obviously, like, it's really hard to catch up, I guess, because you got school. I had to do
Mm.
schoolwork, and yeah. Unfortunately, I couldn't really do much whilst I was there.
Yeah. Yeah. Understood. Okay. Um. Okay. I don't know how much I'll be able to do for this class in particular to get you up to speed because there's obviously a lot of background there. Good news is we are starting another topic of that's pretty much similar to the discrete stuff. So that'll be similar to what you're probably used to with the probability that you do in like Year 11 and stuff like that.
Right.
So that'll be a nice thing to catch up on, and then only maybe in your own time or when we start looking at revision chapters, we can start filling in the blanks on what's going on in here.
Yeah, okay. I just want to ask, what's like the gist with like if I want to book a one-on-one class with you, like how much would it cost?
Yeah, so, geez, what is it now then? Because I think being part of this program means 20% discount on those. They go for 99, so we're looking at like what, $80 on the
Cool.
classes.
Yeah, so does it
Um,
just get billed along with the usual?
yeah, it'll just be built along with that for sure. I will
Right,
point out though, I'm currently full on availabilities. I do have other tutors that are also just as good as me. I've vetted those out.
right.
So it won't necessarily be me for the class, but if you
Yeah,
are looking to, and I'll even give you a trial on that if you're not particularly like if you wanted me, but obviously you're getting a different tutor. I'll give you a
right.
trial on that just so you can see, hey, do you like how this tutor also teaches?
Yeah.
Um, yeah, we can arrange that for sure. So just
Okay.
I'll follow that up after, I guess after this class. I'll send, yeah, I'll get you to let me know your availability for those, and I'll pass that on, and we can start a trial on that.
Cool. Because I'm not looking for like consistent one-on-one because
Mhm.
I'm still in like year 10 and I've got a lot of time to get it up to speed with methods.
Mm,
It's just like I know like integration is like a big part of methods and so is probability.
mhm,
So like and since these are like the two main things I've been struggling with, I just like want to like get up to speed and yeah.
mm, mm. Yeah, understood. Okay. Um, yeah, so a few lessons just randomly to get you up to speed on those. Yeah, I mean, it's definitely doable. Again, like you got a lot of time to make this happen, which is really good.
Yeah.
Um, yeah, yeah. So again, I would say doing like just a one-off lesson on a monthly basis seems like you're not going to get too much out of that. Um, what's probably more effective is sprints, doing short little sprints of like, okay, for this month I'll do 4 classes in 4 weeks, and then that will fully give me everything I need for whatever topic.
Yeah.
And then you do a long break or whatever until you teach yourself the other things afterwards.
Yeah, cool.
That'll be the most effective way to get the most out of it, rather than just doing sporadic things here and there. Sprints are
Yeah, that's
usually a
fair
bit
enough.
more
Yeah.
effective.
Yeah, that's what I was envisioning as well. Like if
Mm,
I struggle again, then I can do that like quick catch up again and yeah.
yeah, yeah. No, fair enough then. So yeah, we can definitely arrange that. I'll just need to know a bit about your availability. I'll find a tutor that's got the right availability to make that happen, and then we'll arrange it.
Right. Because I know like I'm guessing in term four we're going to start doing some like exams and stuff as well.
Yeah, yeah. If you've
Yeah.
seen the
On the
calendar.
unit calendar, yeah, that
Mhm.
thing.
Yeah,
Yeah, so I just want to be like the best prepared for that, I guess.
yeah, sure. I mean, like you'll be prepared for pretty much. I mean, even the calculus stuff. Like I know you said you were having a bit of trouble around the integration, well, up until then. Um, a lot of the exam stuff is you're basically 2/3 of the way through it, I'd say. And even with some of the probability stuff, like you're a decent way. So, well, you got the binomial stuff. I think you were there for binomial and discrete.
I think so, yeah.
Yeah. Um, you're not that far behind, I'll say.
Yeah, yeah, nah.
Yeah.
I got you, yeah. I got you there. It's just I don't want to fall behind even further.
Mm,
Like now that I look back on it, when I was catching up on differentiation, if I had had this conversation back then,
mm.
I probably would have been in a better position now, but
Oh
that's okay,
well,
it's
always
not too far
right.
behind.
I mean, always the earlier you do things, the better, of course. But I will say this is a pretty breakneck pace what we're doing. Like each of the 3 classes are offset off of each
Yeah,
other, doing different things at different times. So it's like it's a pretty breakneck pace to do
yeah,
things in.
that's true,
It was designed in a way where if you can only make one class, then you'll still get through everything.
yeah. Yeah.
But if you can make all 3 of them, then we just blitz through everything. You'll come across these questions at different stages. I know class 3 is a bit of a hybrid between the Unit 3, 4, Unit 1, 2 stuff. So these topics will come up again in Class 3.
Yeah.
So it's not like if you miss it once, you've lost your ticket on that. There's time.
Yeah.
Cool.
Okay. Yeah.
Okay. So what I'll do is I'll put you in a breakout room on this. Is there anything? It'll be probably a bit tough for you to do this normal distribution stuff. Feel free to work on pretty much wherever you're at. I'll have a float around, and then I'll address any of the things you're going through. How's that sound?
Yeah. I'll give it a shot. Yeah.
Cool. All right. So I'll pop you in a breakout room. Okay, that's that. And I'm just going to float around and see where people are at now. Okay. Hello. How's it going, Liam?
Yeah, it's going well, but wait, the topic looks different.
Probably looks different.
Yeah, 16E. Is it about is it in probability methods?
Yeah, it's in probability. So I'll just double check. Are you in the Unit 3, 4 book or the Unit 1, 2?
Oh, I'm in Unit 1, 2.
Yeah, there you go. So Unit 3, 4 book is the one you're supposed to be using.
Oh.
Yeah, so it's still in the Google Drive on the Word doc, so you can still download it from there. But yes, it's the Unit 3, 4 book. But what I'll even do is I'll just do a screen grab of this, and then it's even easier so you can see it. The only thing you won't have on the screen grab will obviously be the answers. So let me chat, send to you, chat, bang. So there's the questions. So that'll get you started there, and then once you start answering a few of those, you can download the actual book so you can see the answers as well.
Okay.
Cool.
Yeah.
All right, cool. So I'll let you work on that for a bit, and I'll come back and see how you're going.
Thanks.
Sweet. Hello. How's it going, Pia?
Good.
Having fun with it?
Yeah.
Nice. No main concerns around what's going on here?
No, not really.
Not particularly? Nice. So is there anything in particular you're working on now?
Could we go through Newton's law?
Newton's method thing? Sure. Okay, let's have a look. Was any questions in particular from Newton's method that were confusing you, or just you want to just do a quick run through of it?
Just a run through, please.
Yeah, certainly. Okay. So for Newton's method, whereabouts was that? Chapter 10H. There we go. Screen share is good. Okay. So it helps to know a little bit about the theory behind what Newton's method is all about. And fundamentally speaking, it's just the repeated taking of tangent lines over and over again. And the idea is, as long as you know approximately where the solution is to your x-intercept, you can take that as some initial position and then take a tangent line at that spot. And what we find is that the x-intercept, so the blue line, the x-intercept of the blue line, actually gets you closer to where you want to be, which is the x-intercept of the red line. And so the idea is, if you say, okay, cool, I started at 4, I got to 9 over 4, what if I now took a tangent line at 9 over 4? That's going to give us the orange line, which, well, I guess yellowish. And sure enough, it's getting even closer. The next natural question is, well, what if I now take a tangent line here? That'll get us even closer, 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 until eventually it's basically overlapping. And that's supported by this table here, which is we started at 4, we got to 2.25, and you see pretty rapidly the numbers stop changing because we get very, very close to that value that we're trying to aim for. Is it clear enough conceptually?
Yeah.
Okay. Now, as for how we actually do it, it's pretty much always going to be a tech active thing, unless they're asking you to create the function, which is like your question 2, question 3 stuff. They're saying create the function and then use it. The use of it is always CAS because it's always decimal. As for how to use it, I like to define it in the CAS in separate stages, each of them defined as each other. So what I'll do is grab the other camera in so we can have something to look at. Let's see, can I move me into this? Looks like it. Take a second to join. In the meantime, I'll just start typing out what it'll end up looking like. And I hope it didn't fully crash, because that's what it looks like it did. Yeah, looks like it crashed. Let me try that again. Basically what I'm going to be getting at is you want to define three separate functions. You want to define f of x, which is the function you're doing the Newton's method on. That's what you see in the numerator of that section. Then you want to define the derivative of f, and you define that as a separate function in your CAS. And then lastly, you would define a final function as what you see here in the Newton's method, where you can think of xn plus 1 as your y equals. Xn is just x. This is your function 1, this is your function 2. So it's going to end up looking like that. To actually show you how to do that, I hope my camera will decide to join. Okay, let's see. Can I force this? We're in room 2. Okay. Join. Looks like it's happening. Okay. Slowly but surely. There we go. Okay, camera's in. So I like to define it as like a of x, b of x, c of x, essentially. So a of x is going to be the function that we care about. So if we use example 33 as an example, our f of x is going to be that negative cubic. So we'll define negative x power 3 plus 5x squared minus 3x plus 4 as our function. Next up, b of x is going to be the derivative of a of x. Now specifically write it like this, so that if you change a of x, b of x will also change as well. Following along so far?
Yeah.
Okay. Are you doing this with me on your CAS, or are you just looking to see how it works?
Well, I'm doing it as well.
Okay. All caught up?
Yeah.
Cool. Lastly is the actual Newton's method equation, which is going to look like this. Define c of x is equal to x minus a over b. And just like that, you have Newton's method in your CAS. So if we now just want to make use of Newton's method, just generically speaking, we need to know where's our rough approximation. So in this case, the book started at 3.8, so we're going to put 3.8 into C. Do decimals on this, the fractions will get pretty nasty pretty quickly. And so that's going to go as 4.99 as the next possibility. All you do from there is feed that back in. And then you feed that back in. And then you feed that back in. And you keep going until you have whatever accuracy you're looking for. So the questions will vary depending on what they're looking for. They might just say find it to a certain number of decimal places. They might ask how many times did it take to get you to that value. Those are the main two things that come up. So if we look and say, for instance, the question was, how many iterations does it take to get to 3 decimal places of accuracy? If we have a look at the table that we have, 3 decimal places of accuracy would mean 532. So 532, 532, 535. Okay. So the 4th iteration in this case would be the answer. 4 iterations to get to 3 decimal places of accuracy. That's pretty much the only main way that Newton's method's even asked questions about, because if they don't actually care about how many times it took to get there, you can just CAS solve it and then just chop it off at whatever number of decimal places you want. So the book's kind of broken in that way, where it's like, solve this to 3 decimal places. And it's like, okay, I could just CAS solve it and chop it off at 3 decimal places. It's more important to understand how many iterations it took to get there. So is it clear why it's 4 iterations in that example I gave?
Yeah.
Okay. That's the main question. The other things that get tested are where Newton's method breaks. I've seen it happen in the past exam, and one thing they said was, why is it that this particular x value is a bad choice for your starting point on Newton's method? The answer is going to be one of these 2 possibilities. The first is that the sequence oscillates, which simply means if I take tangent here, my next tangent is here. If I take tangent here, my next tangent is here, and they keep feeding into each other in a cycle forever, never getting closer to what we actually want it to be. That's one possibility. The other possibility is a terminating sequence, which just means that you took a tangent line at a stationary point. If you take a tangent at a stationary point, it's perfectly flat, doesn't touch the x-axis anymore, therefore it can't continue. Any one of those 2 things is going to be the solution to that particular type of question. Otherwise, that's it for what they do in Newton's method. Was there anything in there you wanted to discuss further?
No, all good, thank you.
Nice. All right, well, I'll leave you with that. There shouldn't be anything in here too crazy. Some of them are a bit of algebra before doing it, but otherwise, yeah, otherwise there shouldn't be anything strange in there. All right, I'll let you play with that for a bit. Hey, how's it going with the correct book?
To be honest, it is pretty hard because I'm actually doing unit 1 and 2 this year.
Mm-hmm. Yeah, it's going to be a bit on the tougher side. Understood. So the few things that you need to be aware of are going to be how to calculate mean and standard
Oh
deviation.
yeah, I did that in general maths.
Oh yeah, okay. Did you do it for binomial?
I don't remember. Actually, no,
Okay.
I didn't.
Didn't? Okay, that's fine. So the 2 calculations you need to be aware of is these 2 here. So the mean is given by n times p, and the standard deviation is given by the square root of all that. So I'd start by writing out those 2.
Okay,
down.
yeah.
Have you got those copied down?
Yep.
Okay. So n is just the number of trials you have in the experiment, or otherwise can be thought of as like your total sample size. So for instance, in example 9, you have a total sample of 1,000, n is going to be 1,000. P is the base probability of whatever the thing is being talked about.
P is the probability. Okay.
And so as soon as you're able to identify those 2 things, you can now calculate your mean and standard deviation.
Okay, yeah. Hold up. Sorry, I'm gonna write this down again. Okay, got it.
Nice. Okay, now from there, this is where we have to now use the CAS at this point. This topic is entirely based on CAS because we have to use the CAS functions to achieve those. So what I'll do is I'll bring my camera in and pray that it doesn't crash, because apparently it sometimes does, which it did not do this time. Awesome. It'll just take a few seconds to come in. Do you remember where the normal distribution functions were? That's fine.
Yeah, I forgot.
Do you know what CAS do you have? Is it this one?
No. I'll just turn our video on. Oh, sorry.
You've got basically these two options, either the Casio or the TI Inspire.
Okay, so it's this Cas.
Yeah, you got Casio.
Yeah,
Okay,
Casio, alright.
that's fine. Let's have a look. So, for the Casio, what you're looking for in particular is going to be under interactive and distribution on the calculator window.
Okay.
So, do you know how to get to this thing?
Is that the main menu?
Kind of. So if we go to the menu,
Oh yeah,
it's
sorry,
up
yeah,
here at
main.
Yeah. We're going to hit interactive. We're going to hit distribution.
Oh, okay.
And we're going to hit continuous.
Yes.
We want norm CDF. Once we hit that, we just need to know what the lower and upper bound is of our scenario, the mean and the standard deviation.
Okay.
So in our example that we had earlier, it was 300 for the mean, so we'll type that one in. In this case, we had a standard deviation of root 210, which...
So which one's lower, upper, and?
Yeah, so we'll get to lower and upper in a minute. We'll just put in the standard deviation. Lower and upper are going to come from the... what is it? Lower and upper are going to come from, if you look at the screen share, it is the domain that's associated. So between 270 and 330 tells you lower bound is 270, upper bound is 330.
All right.
So yeah, we'll just put that in actually. 270, 330. Yeah, I got to remember where the root is. Root. It's not quite that one. I guess it is kind of. So that's going to be, where is it? It's the square root of 210. That should probably work. And then yeah, that's going to give you the value, which looks like it has worked. 0.9615, 0.961, yeah, okay. Cool, just round.
Okay, so what is like the standard deviation and the mean?
Yeah, so standard deviation is square root 210, if you have a look at the screen share.
Really? Okay.
And the mean is the 300. And that's just by calculating with n being 1,000, p being 0.3.
Okay, wait. Can we see? Okay, and it means 300. Okay, so 0.961566.
Yeah, that whole string is the final probability of this scenario.
Okay then. Yeah.
Cool. So yeah, in total, you want to calculate mean and standard deviation, which means you need to know n and p. From there, you go to interactive, figure out, I'll plug that into the correct spots for those. And lastly, all you've got to do is figure out the associated upper and lower bound.
Okay, and then find this. Yeah. So I can calculate the mean and standard deviation.
Yeah, well, you need that at the beginning.
Yeah.
Then you put that into normal distribution to get the probability.
Okay.
Nice. Only thing I'll touch on is you have to now make sure that you handle things based on how you handle continuous probability, which is even though you have n equals 100 in question 1, your upper bound you still take as infinity, even if it doesn't make much sense. When it comes to normal distributions, you still have infinities either side of things.
So what do I write for upper boundary there? Like how do I like the infinite symbol?
Yep.
So,
okay. So let's bring it up. Get distribution, continuous, norm CDF. So for lower bound, we know is going to be it's more than 10, so 10 is the lower bound for this one.
10.
Now for upper bound infinity, what we're going to do is have a look and see if we can find it. It's in math 3 right there.
Oh, math 3. Okay then.
Yep. So that'll be that. Standard deviation we have to calculate, mean we have to calculate, but yeah, if you have to use infinities, then you'll use it in math 3.
So like number of trials is 100.
Yeah, number of trials is 100 in this one.
And probability is which one? I don't know.
Okay, well it's saying what's the probability of more than 10 sixes, so what P is like the fundamental, like individual probability, which is what is the probability of getting 1 6?
Oh, okay, 1 6.
Yeah.
1/6.
1 over 6, correct. So you'll see, even if we compare to this one here, it's like 30% of people are in favor. So 30% for any individual person, and then you expand that out across the full 1,000. Same thing over here. 1 out of 6 for 1/6, and then we expand that out across the 100.
Okay.
So that's the difference between P and your final answer.
Okay. Okay, so sorry, what is P again?
P is that like fundamental probability, which is probability of one given event occurring. So for sixes, it was a 1 out of 6. For people being in favor, it was a 30% chance. It's like in the entire sample space, what's the probability of just one of those things happening?
Okay then. Yeah. Okay. Thanks.
Yeah, so I'll do a few more examples just so you can have it. So for rolling a 6, it's a 1 out of 6. For being in favor, that's your P. 50%.
Okay, so
10%.
so like 1 over 6 times 100 there?
Yeah, that would be for your mean. 1 over 6 times 100.
Okay.
Yeah.
Okay. And then standard deviation.
Or standard deviation is going to be that equation that you wrote down with the square root.
Oh yeah, my bad. Okay.
The square root NP, which is the mean again.
Number chart. So 100 times 1 over 6. 1 minus 1 over 6. So 100 over 6. 5 over 6 times 5 over 6. Oh, your root 536.
Yeah, I didn't actually calculate. Yeah, probably. Yeah, 500 over 36 sounds about right.
Yeah.
I would just do it all in one line in here. It's not too crazy to do that.
Yeah.
But yeah, you just hit OK on that. Oh, incorrect number of arguments. What did I do wrong there? Oh, right, I didn't do my brackets properly. That's my fault.
Okay then, yeah.
Let's try. Is that good? That should be good. Yeah, there you go. And so for that one, you would have got pretty similar to me, right? 0.9631.
Wait, 0.9631. Yeah, got it.
There you go.
Mhm.
Yeah. So that's the first one sorted.
Okay.
Yeah, give a few of those more
Yeah.
of a shot. See if you can do some
Okay.
yourself, and then
Yeah. Thank you.
no worries. I'll
Yeah.
leave you to it.
Yeah. Thank you.
Hey, how you going?
Oh, good. How are you?
Yeah, doing fine. Did you come up with anything you want me to have a look at?
Like, as in with integration or like
Yeah,
with the.
with anything where you're up to. Yeah.
Honestly, like like there's the rules of like converting specific functions when we're integrating.
Oh yeah.
I know the power function rule, but I would like some clarity with the other ones. That would help.
Yeah, no, certainly. We can definitely do that.
I know them all for differentiation now, including like the specific to function ones, but integration, I think I still need to do some work with that.
Well, it's good that you got the diff ones down, because the integration is always going to be the reverse of diff, right? And
Yeah.
so that's one thing that you can have in the back of your mind to remember, that it's not going to be all that much different to what you're used to.
Yeah.
So let me pull up the notes on that. We can have a bit of a discussion, and we can have a look at a few.
I remember when I was doing diff earlier, right, when we started,
Mhm.
I used to just refer to the table, but that was like slow and cumbersome, and when I actually like fully like remembered and memorized the table, I found it much more easier to do the work, I guess.
Oh, well, sure. I mean, in both cases, you're still using the table. It's just one of them's in your head and the other's on paper.
Yeah, because when you have to like look back, I feel like I just lose my train of thought when I'm doing the question.
Sure, okay. Yeah, I wonder if you can arrange your desk or workspace in a way where you can see both at the same time. And maybe that, yeah, I don't know. I mean, that, or it might be better to do like just full drills on each individual one at a time. And the textbook supports that. If you've got the copy of the Unit 3-4 book, you'll notice, where's integration? I went too far. So integration of this particular function integration of, well, it does sort of skip a few, hang on. Integration of roots, integration of circular functions. It does individual versions of each of these. So that will be a good thing to do when you're doing your own private study. But as for what's going on here, it is still the same thing as diff, basically. So you just want to get a match on the left-hand side thing and then replace it with the right-hand side thing. There's lots of division in integration, just like there's lots of multiplication in diff. So if we have a look at a few possible examples, we'll ignore the hyperbola one because that's real crazy for now. We'll just focus on some of the easier ones, which will be something like anti-diffing e to the 2x, right? So e to the 2x, normally if you diff this, its power, you grab the coefficient here and you just chuck it down the front, normally, yeah?
Yeah.
So for integration, it's the opposite, right? So instead of bringing this and putting it down here, now you want to put a division down here instead, which you can look at and compare over here, right? So you identify what's your A, what's your B, and you plug it in those spots. We only had AX, we had 2x, which is why we're going to put a 1 over 2 out the front there. Cool enough?
Yeah.
Yeah. So it is still just like looking at the table in those cases. It's just going to take a decent amount of practice, realistically speaking. One thing I can say for a bit of self-correcting is try to diff this back into that. Because if you can diff and get back to where you started, you've done it right. Because you've said that your diff is in a good spot. So when you're doing your integration, diff your result, see if you get back to where you started.
Yeah.
But otherwise, yeah, that's just exponential. Graphing isn't really what you want to do. This is a bit too crazy. Maybe we'll just pull up a few of these. So you'll notice for like sine and cos, for instance. So the sine one is just whatever the coefficient is in here goes as a division, and then everything else pretty much stays the same. Obviously, you're going to flip your sine and cos, but like we know that cos goes to negative sine, so when you start at sine, going backwards the other way in integration, it'll be negative cos. You don't have to have any of these memorized, by the way. You can have, because it is in your formula sheet, it will be on any SAC or exam that you do.
Right. Yeah.
So don't feel like you have to have it memorized. It is obviously faster and you will just sort of have it memorized anyway. But I wouldn't like go out of my way to try and dedicate time to memorizing it, more so applying it.
Yeah, for sure.
But yeah, so literally just, we can identify its sign, it's comparing to this, so figure out what your k and a are. In this case, k is 3, a is positive pi over 4. And so you just look on the other side and be like, okay, so negative 1 over k, negative 1 over 3. Kx, 3x. A, pi over 4. C, C.
C is just like, I remember we don't do anything for that one, right?
Yeah, in a lot of cases you don't do anything with it. It's just there to stand for any possible constant that could have existed. There are some circumstances where you'll be required to solve for C, and that'll be what this one would have been if you know additional information about that original function.
Yeah.
So once you get your anti-diffed function, you sub in that point, and that'll allow you to solve for C.
Right, cool.
But otherwise, yeah. Otherwise, final answer will have a plus C in it. Okay?
Yeah.
That's circular functions. Let's have a look there. I know one of them doesn't actually have a chapter section because the chapter broke. Where is the... Maybe it's down lower. It wouldn't be lower than this. Probably this, 11D. Yeah, 11D didn't have one. But we already talked about exponentials already, so I guess that's fine. This is where we start getting the hyperbola type stuff. So I'll talk a little bit about why it's weird. You don't need to really know why it's weird, more so just, again, use what you're seeing here. But I think it helps to know a little bit about why. So there's more memory anchors into like, oh, okay, so we got to do this. Got it.
Yeah.
So first things first, anti-diffing a hyperbola gets you a logarithm. The reason why that's a problem is because hyperbolas are defined for all real, whereas logarithms are defined for only positive in the brackets. So if you were to try and do your integration, you would have to either create two separate antidiffs to describe both sides of that equation, or you would have to use this absolute value sign, which just means instead of doing curved brackets, you do straight line brackets.
Yeah. And this means it can only be positive, right? The
Yes.
absolute value.
Yeah, so it basically means if you put a negative number in there, the negative just gets knocked off and you pretend it's positive.
Yeah.
Like literally speaking, this description here means these two dot points combine into one.
Cool.
Same thing over here, right? Absolute on this, same thing as just rewriting that. So that's the first reason why there's a bit of weirdness. The second is that you'll find that, and this isn't really actually even taught in the formula sheet, so this is a thing you'll have to be at least somewhat aware of, which is integral of 1 over ax is different to 1 over ax plus b. The easiest way I can explain what's going on there is if you think about the diffs of those functions. So if you diff the 1 over ax sort of situation, wait, what am I saying again? It is sorry, diffing the log, right? So if you have log ax, you're going to get to 1 over x. It doesn't actually matter what the a is; it always gets cancelled out.
Yeah.
That's clear enough to move on from.
Yeah.
Now, when you have 1 over ax plus b, that doesn't happen anymore because now you've got this plus b in there. That means you can't just kill the a. And so for that reason, it doesn't actually simplify in the same way that the 1 over ax would. And so for that reason, the integral, doing the reverse of what we just did, they're going to have two separate integrals, which is why if you look at this one, 1 over ax, there's no a on the x here. Ax plus b, there is an a on the x plus b. Cool?
Yeah.
Yeah, so it's just explaining a little bit about why there's no a on this x, whereas everything else in the formula sheet has an a there. This one's special because of what I just described. Yeah, and so fundamentally, all you really need to do is do these two black dot points. That's the minimum standard for what you need to be able to be aware of. This is if you want your answer to be super nuanced, which is instead of always going absolute value, if they only give positive or negative domains, then you can show a bit more expertise by saying, well, actually, I don't need to use the absolute value because my domain isn't negative or isn't positive, so I can just use one of these instead.
Cool.
Just while you're learning it, don't bother with this. Stick with the two black ones, and then you can start using these and understanding what's going on there. Just minimize the amount of effort you have to put into any given stage.
Yeah, right, fair enough.
That's a bit of an overview there. I'll stick around and see. Is there any one of those you wanted to practice?
Well, honestly, I like the first one, the ax plus b.
This here?
Yeah.
Yeah, okay, that's fine.
Because
So
I've got to leave for training in like 5 minutes, but if we can do
sure.
one,
Yeah, if we
I
can
don't
do one of
mind.
these. Yeah, okay. So we'll do one of the ax plus b's, which is this. So I'll grab a screen grab. Do you have a copy of this already?
Of like the
This
note.
table.
No, I don't.
Okay, that's fine. I'll just grab a copy of it now. Send it to you. Let's have a look at this one here. So I'm going to try and get my camera in here. It does take like a minute or so, so let's hope it doesn't crash. Where am I? There we go. Move this into there. While that's loading, have a think about what you might do for 1A.
Is it 2x minus 1 to the power of 3 over 4.
All over 4. 3 over 4. Probably not, just by looking at it, because this is going to raise up by 1, and then this 2 is going to come down in there as well. Because if you look at what's going on here, n plus 1, that's good. That's 3. So you're going to put a 3 here. But there's also this a, which is 2. So that's going to go down as a multiplier on the denominator as well.
So, wait, hold on, my bad. So would it be 2x minus 1 to the power of 3 over 6?
Over 6. Yeah, that's better.
Yeah.
That's pretty much it. So just figure out what your a, b, and n are in the left-hand side, and then put those in all the spots that you see a, b, and n.
Okay. Can we do one for the rule below it?
Yeah, exponential. Sure. Let's see. I mean, all the exponentials are going to be more or less the same. There's no complicated version of it. There's just longer, more of them. So if you were to do like 1a in that case, e to the 6x,
Is it e to the 6x over 6?
yes, it is. Yeah, precisely. Whatever the letter is up here, bring it down. Even if there's a plus b, we don't really care. We just keep it where it was.
Okay. And then like if there's like one next to it, like is like I think it was e to the power of 2x plus 3x. We just need to do the integral of both of those, right?
Yeah, you do them individually.
And is there like a rule for this, or just you gotta add them?
Well, you do the x version for the x one. So 3x is the same as your x power of n. And e2x is what we just did, e. So if you have, if you
No,
have
I was
two,
like in the sense of like how we have product and quotient rule, but
oh,
this won't be a problem, right? It's just
no,
the
no, no.
addition of the integrals.
Yeah, so plus minus is all you ever get. Whenever there's division, there's always a way to get it back to plus and minus.
Yeah.
So in this case, it would just be factoring the ex into both of these. So you won't have to worry about like product quotient rule stuff when it comes to this.
Okay.
All right, cool. That's about all we have time for today. So I'll just kill the breakout rooms and then I'll just close out the lesson on this one. And if there's anything else I can quickly clarify for you after class, we'll do that.
Yeah, that's
Sound
okay,
good?
but thank you for the help. I really appreciate it.
Yeah, no worries. Okay. How we all go? Is there anything final that I can have a look at for anyone? If not, I'll happily let you enjoy the rest of your day.